My name is Giovanni Gherdovich. I work at SUSE here in Prague. And for the next 50 minutes, we will explore, we will have a look at a new kernel feature that will be released early December in Linux version 6.12 that let users write their own CPU schedulers as a loadable BPF program. And so let's get started. What are we talking about? As I said, this is not my work. The author of this feature is a gentleman, two people, Tejun Heo and David Vernet from Meta. And the crux of the matter is that this feature will expose the CPU scheduling operation to BPF. BPF is, for those who are not familiar, is a virtual machine in the kernel, and it restricts the operations that a module can do, but is essentially very similar to a kernel module. And so what we will be able to do once we get this kernel 6.12, although there are already builds, for example, you can install the release candidate in Tumbleweed, in OpenSUSE Tumbleweed, which is the community distribution that I also contribute to. We will be able to write our own CPU schedulers with BPF. Why not? And you will write your BPF program. You will load it. It will take charge of scheduling the threads of your system. And this can be loaded and unloaded at runtime without needing to reboot the machine. You don't need to recompile the kernel. You load the BPF program, and you're in charge of scheduling. So why would you want to do that? This is a very legitimate question. In my view, there are three main motivation. One is for education, a student at school, at university, or a person that is learning on their own. They want to experiment with task scheduling. And with this framework, they have a more ergonomic API, a more ergonomic programming environment to write a scheduler and see how it works. And so it is a gateway to system programming that is very rewarding. So another aspect is academic research in the domain of scheduling, which is also presents theoretical problems. And a researcher may want to explore new algorithms or do performance evaluation of some idea. And in this way, an academic that is not necessarily versed in the internal of the core kernel scheduler can use this this framework to write a scheduler. And not least, there is an interest when it comes to performance, because the CPU scheduler that we have in the Linux kernel is essentially one. There are, it's maybe more correct to say that there are three, but the one that almost every application uses, which I will call the fair scheduler, is essentially a single algorithm that needs to accommodate the needs of every application, from desktop application to server application or to embedded, and all possible types of hardware, mobile, desktop, big servers, etc. And so necessarily it makes some compromises in order to serve those different needs well. But what if you could afford to write a task scheduler specifically for a single application that you care about. That could be a particular video game, it could be a database or a web server, and you don't have to worry about regressing all the other kind of use case that is the case when you patch the main scheduler, but you only care about your specific use case, and you can afford to ignore everything else and your specific hardware. There are, you may have an Intel CPU or an AMD CPU. They have different peculiarities. And you could leverage the particular hardware you care about and make all the assumptions you want, because this is your own scheduler. And so if you are able to do that, you may, and this is still early days, but you may have a better performance. You can use your hardware more efficiently. So those are the three cases that I generally see for this type of technology. What I will explore in these few slides that I brought to you is the plumbing, the infrastructure of this framework, so that my goal, my objective is to give you the context that you need to understand the rest of the reference material and potentially get started experimenting with this framework, or simply have an informed opinion on what exactly it is. But as I brought in this slide, the exploration of the API is the easy part. I mean, the hard work has been done by the software engineers that developed this at Meta, which is the company that runs Facebook. But for us, that we get this framework, all right, we learn what is the API, but the hard part is to understand what your application is doing. So tracing your application, develop an algorithm that suits your particular application, which is not something that I'm going to treat in this talk, but I would like to stress that this is the hard part. So the hard part is tracing, understanding, developing an algorithm, while what we are going to look at is an inventory of the mechanics of how this happens in this future kernel version. So before, just a second. Before we get to the architecture of this framework, I will give you potentially a refresher, or if you're not familiar with the operating system scheduler, a briefing of what's the business of scheduling. So what I draw here is a diagram of the different states that a thread can be in. I wrote thread. I may say in the rest of this presentation, I may say task, which is a deviation that is usually utilized in kernel development. When in the kernel source thread are called tasks. So I will use those two terms interchangeably. So a thread can be running or sleeping, right? So if it is running, it is in one of those two green boxes. It could be running in user mode or in kernel mode. You run your application in user mode. At some point, you invoke a syscall, and you are in kernel mode. Now, this is a thread that is on the CPU running. But threads can also be sleeping, and in which case, and how do they go? How do they go to sleep? At some point, your thread may need a resource, for example, the disk, packet on the network, maybe waiting on a lock, and needs to wait on it. So it has nothing to do because it needs this resource to arrive, so it can't make any progress, and so it relinquishes the CPU. And so it goes out of execution here, and this is called going to sleep. At some later point in time, the resource that he was waiting for is going to become available. So the thread will then, the terminology that is used is the thread will wake up. So the thread is wake up, and now it is runnable. And it is in this runnable state, and when it is runnable, it is inserted in a data structure that is commonly referred to as the run queue. So it's a wait queue, it's a queue where you wait for your turn to get some time on the CPU. So we were going out of execution from kernel mode from this spot here. We were going to sleep, but there is something else that could happen, which is going out from this part here, and this is not voluntary as in the other case. It is involuntary. It's the scheduler that says you have exhausted your time slice, and you need to make room for some other process. So the execution of the thread is interrupted all the time because the threads need to take turn into running on the CPU. So remember that this is going out from here is sleeping, waking up from this part. This other loop instead, so being taken off the CPU involuntarily and then returning on the CPU, it's not a wake up. This is a voluntary context switch, and this is an involuntary context switch. So you can become runnable while you wake up, or you can when it's again your turn of running on the CPU. And the job of the scheduler is to take all the guys that are here in the runnable state and arbitrate the rare resource, which is CPU time, and according to some policy, to some scheduling algorithm. So when does scheduling happen? Is there a program that is called scheduling? No. If you write user space application, you don't realize that because you have the illusion that execution is continuous. But if you write kernel mode code, it's more apparent that at some particular point of the execution of a thread, a particular function that is called schedule, it's a function in the kernel, is invoked. And it is invoked in very specific canonical situation, which is returning from a syscall. So your thread was issuing some I/O request, I/O is ready, and so you do I/O with a syscall, and then when the syscall is so when you are in the syscall, you are in kernel mode. Syscall is over. It's about to return to the user mode code, but the kernel says, wait a minute, I will invoke the scheduler and see if there is anybody else that needs to run. The second opportunity is returning from an interrupt handler. Interrupts are, it's a hardware concept. The CPU gets notified of something that happens, packets arrive from the network, a key from my keyboard is pressed, and so execution immediately transitions to the kernel to service that interrupt request. While after the interrupt handler, which deals with this request, is over, again the kernel says, wait a minute, this could be a good time to invoke the scheduler and to see if there is anybody in the runnable state that has more need of the current thread to run. So the scheduler is invoked at these two at these 2 points when you return to user space from a syscall or from an interrupt handler. There are a few more cases, but I think for the moment we can limit ourselves to these 2 particular cases. And now I'm going to introduce you to scheduling classes. Here, classes is a term that is borrowed from object-oriented programming, even though the kernel is written in C, but there is sort of a pattern of coding where you have classes and methods. Methods are function pointers and classes are struct. But what I want to stress here is first that there are a few classes, 3 for the moment, and the ext or extensible is the one that is added. And so this is what I intended when before I said in the kernel there are, it's correct to say, it's more accurate to say there are 3 schedulers, but the one that almost always used is fair. The fair scheduler, but there's also deadline, which is a sophisticated real-time oriented scheduler that is suited for periodic work. And then the real-time scheduler, which is rather trivial and essentially you take an application, you put it on the CPU, and you never stop. You let it go as long as the application wish. I'm oversimplifying. There is also another declination of this real-time scheduler, which is round-robin, but essentially real-time is a trivial scheduler. Fair is the one that we all know and love since 15 years ago. It used to be implemented with an algorithm called CFS, completely fair scheduling. Recently, the algorithm has changed, but this is the 3rd and most used scheduler. So I said that in the kernel there is this concept of classes of the scheduler, and what in this with this feature we are adding one more class, and the methods of this class, to simplify a little bit, are essentially exposed to BPF. So it's a class that is a wrapper, gives you some callbacks that you can implement, extensible. So the 3rd aspect that I want to stress from this slide is the order in which those classes are in the slides. First is deadline, 2nd real-time, 3rd fair, and 4th is the extensible. Now the order is important because they are searched in this order. As I said before, the scheduler is invoked at some canonical points, roughly speaking, returning to user space. So you call schedule, and the function schedule goes looking at those classes, and here I mean the group of threads that are served by each of the class. So it goes looking to deadline. Is there anybody that needs to run in deadline? Like, is there any thread in deadline? Any thread at all? No. Okay, next one. Is there any thread at all in real time? No. Is there any thread in fair? Oh yes, there are two threads in fair, and I'm gonna pick one. And so this is your scheduling cycle. Next time, schedule is invoked at the next return to user space or whatever, and it starts again the search from the top. So you can see that if you are toward the bottom of the hierarchy, you never get invoked. You never get a chance to run, right? So the extensible scheduler, which we are treating today, is in a rather unlucky position because it's the last one. Essentially, it never runs unless the machine the CPU is idle. Everything that I'm saying here, I am thinking of the schedule function as invoked from a CPU for that CPU. Then you're going to have 12 CPU, and each of them has its own schedule function. It's not like schedule is a global thing. It's every CPU invokes like threads. They run on a given CPU. So extensible never runs. OK, that's not very good news. And it was a design decision. As you can see, there are not many choices. Like, where do you put it? Like before fair? So you starve fair? No, the developer decided to be polite and be after fair by default. But if you if you set a particular config option that makes it usable at all, then the extensible class will also take care of all the fair tasks. So you write your own little scheduler in the extensible class. You set the switch all, which is the config, switch all to true, and then you're going to get the thread that you set with your syscall set sched, something like that. You set to extensible, and also all the thread in fair. The thread in real time and real time, those stay served by the respective classes. There are some kernel threads, like housekeeping kernel functions that are in real time. You don't want to mess with those, so you leave them there. But extensible takes care of fair. So this is how it's implemented. Now, you can't talk about a class in the object-oriented sense without talking about methods. So the framework that is in the kernel before this particular extensible class, but the framework lets you define a scheduler class. As we saw, there are 3, deadline, real-time, fair, and the new one's extensible. So you have this class, and you have to implement a set of methods, right? So it's sort of like in Java, you have, I don't know, virtual classes, whatever, I don't know. You have some method that you have to implement. And it's the same here. The scheduling framework, the core scheduling framework requires you to write your own enqueue task. So you have to write your own logic here. So the algorithm of the sched class goes in those methods. Enqueue task, so put it into the run queue. Dequeue, remove from the run queue. Yield, relinquish the CPU. So you have to implement those callbacks. And this is a long list of callbacks. This slide is not to make you like memorize or look at all of them, but it's just to give the sense that a scheduling class, such as extensible, needs to implement those callbacks. And in one way or another, we are going to be put in charge of those, in some sense. Not directly, but in a rather indirect way. But that's the thing. Like the code that we are going to write, sooner or later, is going to be executed by the enqueue task of our extensibles class. Okay, so this is just to give, to put things in perspective. So this diagram, I didn't make it. I took it from the slide of the author of this work, Tejun Heo from Meta, which had the presentation last month at the Linux Plumbers Conference, and is explaining in a very eloquent way the characters of this story, which I will introduce. I'm not sure if it's visible, but so we have the scheduler core. Scheduler core is the framework that lets you define those classes, etc. And then you have Sched-Ext core. Sched-Ext is our framework, this extensible class. This is a new thing, okay? So you have Sched core, then Sched-Ext core that talks to Sched core, right? And then you have your own code. So your own code is here. Your own code is here, and the thing to notice in this slide is when I said I want to give you context. I'm going to give you context to understand reference material. The context, one important bit of context is this. enqueue means that the frame or the core framework is giving you a task to take care of. And when you're done with all your magic algorithms, you dispatch it, you send it back, say, run it, right? So enqueue, you get a task, dispatch, you send it back. And obviously, you get many tasks, you do all your sorting, all your data structures, all your red, black tree, and whatever, and then you select the one that you want to make progress first, and you tell the core framework to run it using dispatch. So it's important because, like, if you would expect enqueue, dequeue. No, it's enqueue on one side and dispatch on the other side. It's the way it is. So remember this. Those are enqueue and dispatch callbacks that you have to implement in BPF. Then there is some, okay, so this is our program, and what's this guy over here? Like BPF is, as I said, similar to a kernel module. It's a virtual machine. You write some C code that gets compiled to bytecode, and that gets run in this virtual machine in the kernel. But what's the user space story here? User space is a tiny wrapper that you have to write, make around your little module to pass it like command line option and stuff like that, right? So this is like 50 lines of C or 20 lines of C, or Rust, because those wrapper languages are C or Rust in the framework that are that is gaining momentum, like them. So this is a tiny program that you have in user space that sends that you start your scheduler, and you give it some like max minimum time slice, whatever, stuff like that, and those information that get sent to the kernel module that you are remote controlling from user space via BPF maps. BPF maps, it's a data structure that is understood by BPF. What's important to know here is that in order to communicate via BPF maps, this involves a syscall. The syscall is called BPF. So remember that, because later, if I get to that slide, I will also show that there's also another style of programming in this framework, and the style is, can you see my pointer? Yes. The style is that, okay, this is supposed to be your algorithms, right? Over here. What if, so Sched core is exposing you callbacks that you can call from BPF. How about BPF itself expose this stuff to user space? So at this point, you can implement your algorithm in user space, which is pretty cool. Like you could write your scheduling logic in user space, floating point arithmetic, all of that kind of stuff, and the comfort of developing with the tools, like you can write, Rust or I don't know, any other language that you like. I mean, at the moment, the frameworks are for C and for Rust, but you have that sort of change, build, run workflow that is comfortable, and you don't need to, in order to change your algorithm. So this is something that can happen. But in order to do that, you can't use maps, because maps, like every time you have a context switch, you would call a syscall in order to know who's next. And that is not efficient. And so in that way, you don't use maps. There are two ring buffers that you would use. But I wanted to stress that. So what else to know about this slide? Yes, so Sched core, we know that. This is the old stuff. Sched-Ext, new framework that let you write your own code. BPF scheduler. So here you see DSQ. What is this guy? DSQ. So DSQ means dispatch queue. And it's a data structure that the framework offers you that you can stuff the task into. Like it's a queue, can be a FIFO, or can be a priority queue. And you do what you want with it. Like you can create as many as you want. For example, you may want to have like a DSQ per C group, or a DSQ per, in the recent AMD CPUs, you have core complexes, CCX, so that are, topologically, they are composed of multiple cores, but it's not like, it's a little less than a node. So you could have a DSQ for that, like for each of CCX. So you can create as many as you want. And so those are your DSQs that are in your BPF scheduler. And but in BPF, you're not limited to using those queues. They are there because they are actually implemented in the core, and you can use them. But you can also use BPF other BPF data structures. There are not that many. BPF is a little limited. It's expanding, but it's a little limited in the expressivity that it does, because the strength of BPF is the verifier, the fact that you can't crash the kernel with a BPF program. So, but BPF has lists, associative like arrays, and recently also red-black trees, which is something that you could use to implement a priority queue. So you can use DSQs, you can use something else. All right. There is something that in this slide is not is hidden, but I'm going to show you in the next slide. But it's important to know. So let's get back here. So you have your BPF scheduler and you dispatch. You send the task over to the core to like run it, right? Well, there is the core, the Sched-Ext core has a DSQ. It's called a local DSQ per CPU. Why is this important? Like, why am I telling you all these details, all these implementation details about like this framework? Because if it's context that, like, if you don't know that there is a DSQ that is receiving your task, you don't understand the comments in the code. Because they say, oh, I'm dispatching to a DSQ. What? Like, my DSQs are here. Why are you dispatching to a DSQ here? There is none. Yes, there is. Those are the local DSQs, which are like the, I don't know, it's like when the bus hits the last station of the terminals. Terminal, exactly. The local DSQ is the terminal station of your task. And those are artistically represented in the next slides, which is this. Poof. So I have 4 CPUs, and each of them has their local DSQ. So this slide is very simplistic, but I want this idea to stick in your head and to stay there, because if you intend to look at the documentation, which is a little scarce at the moment, but you will, you need to remember that, oh, local DSQs, all right. So there are all the DSQs, but the local DSQs, which is 1 per CPU, are special, okay? And yeah, and the objective of like your algorithm, the objective of your algorithm is to put tasks into those. Like, you will see that I will try to show you the different callbacks that are available, and the goal of the game is to put the task into those. As far as, so remember, Sched core, Sched-Ext core, your scheduler. As far as Sched core is concerned, those are the run queues. For you, it's already out of your control. Like, they have an order, they FIFO, you send stuff, and it's done. But from the point of view of the Sched core, those are run queues. And so they pick tasks from, in a FIFO fashion, from those. Next. All right. So, so this is a slide full of text. What I mean with this, like, what is the message that I want to convey? Obviously, this is a wall of gibberish, right? It's all the name of the different callbacks. What do I mean? So on this side, on the left, you have the callbacks of a scheduling class. For example, the extensible one, like all of them. All of them, they have to implement those. And on the right, you have the callbacks that you have to implement in BPF. So, so this, for example, this one is, I highlighted the one that I will refer to later, but select CPU is an important one, so you need to write code for that. So in your BPF code, you have to write the code of it, and you will receive very nice task struct, which is a struct that contains all the information about the particular task thread. like all the stuff that defines the thread, right? And then you have the previous CPU that the thread was running on, because in this case it's just woken up. So this is the CPU that the task was running on, and those are some flags. So this is all stuff that you can use, and you have to use to implement your algorithm, right? And of course, in one way or another, the Sched-Ext core, which is the guy that is exposing those callbacks to you, will call this select CPU from one of those, right? In particular, it's this one, select task RQ. So the Sched-Ext core is doing some logic that it needs to do, caring about all the locking that you don't have to care about, which is very important because it relieves you from the need of knowing some intricate locking conventions, like, oh, you cannot call this function if you don't have that lock, if you don't call, etc. You don't have to care about any of that. The Sched-Ext framework does it for you, and once it's done with all this expert synchronization manipulation, it calls your code here. Right? So in particular, this calls that. It's not always a one-to-one correspondence. For example, enqueue is called by both enqueue task and put prev task. So like it's sophisticated, but the thing is that the thing I wanted to convey is that the code that you write, one way or another, is going to be invoked by the callbacks. Another important one is dispatch. Remember dispatch. Dispatch is important. Dispatch is when you send back the task to the core, is invoked by balance. Load balance invokes the dispatch, right? Anyway, so those are the callbacks that you have to invoke. There is another. I wanted to highlight. You don't need to, by the way. Depending on the sophistication of your algorithm, you can leave some of them, all of them, empty. In fact, the only mandatory parameter is name, which of course is not going to be very interesting. You write a schedule that has only like a name that, I don't know, Fred, okay? And the framework will give you a default implementation for select CPU. It will do nothing for all of those, and it's going to do probably something not very interesting. Probably some FIFO scheduling, something not very sophisticated. But you don't need to fill all of them, right? So, yeah, I wanted to point that out. The important thing here is timeout. Timeout is interesting because it reminds me that the BPF machinery, the Sched-Ext core machinery has a watchdog functionality that will unload your scheduler if it is not scheduling anything for more than timeout milliseconds. So I don't know, you set this to 5,000, 5 seconds, okay? So if the watchdog detects that you are not dispatching anything for 5 seconds in a row, you're out. So the scheduler is unloaded, and the default scheduler, which is fair, is going to be reloaded. Okay? So this is a safety, it's a fail-safe mechanism. Then this is again for the purpose of giving you context. Wall of text. What do I mean by this wall of text? So I have to write my select CPU. Like, how do I do that? I have to enqueue. Like on select CPU, I got task struct, etc. Task struct. Like, what do I do with that? In my BPF environment, I don't have access to all the kernel functions that can manipulate scheduling. So what you will use is what is called kfuncs, which is a way for BPF to call a set of kernel functions that are annotated for that, because BPF cannot call like function at random. BPF is supposed to be a secure environment. So in the Sched-Ext framework, they say, okay, we're going to give our users a set of callbacks to write, and we're going to give them the tools to write those callbacks. And those tools are the helper function, kfunc, and there are a few of them, right? So before we saw that there are the Sched core callbacks implemented in terms of our Sched-Ext callbacks. And now there are Sched-Ext callbacks that we have to implement using those kernel functions that are available as an exception. And they all, I mean, you recognize them because they are prefixed with SCX BPF. And I want to point that out because in this slide, like if, okay, this is an important slide to remember because if you want to get some documentation, some authoritative and documentation on what to do with your callbacks, those are the callbacks here and the kfunc here. You have to go in the source code of Sched-Ext, which is like kernel source, kernel/sched/x.c, and look for those functions and the comment that is on the top of them. And this will tell you what they do. Like there is another way at the moment. I mean, it's, again, early days. So those are the helpers that you want to use. And your enqueue function will have a bunch of, I don't know, C code. And at some point, is going to call some BPF consume, BPF dispatch, etc. Okay. So this is the most important slide of the talk. We have 10 minutes left. Let's go. You can't read it. I know that. And for this, like, is that? Can you read that? Yes? Okay. So what I want to illustrate here are the two most important situations that in the scheduling cycle. Again, this slide is not mine. This is like before. I took it from someone else, David Vernet, okay, OSPM Summit 2023, and because they've been working on it for a while. So what are we seeing here? So without seeing anything, here on the left we have wake up flow. Wake up, remember wake up? Wake up is when you go out of the CPU voluntarily and then you're ready to run. Wake up is not when you exhaust your time slice. So wake up, okay? And this is when schedule is invoked. So when schedule is invoked, this is gonna happen. Those are this is the callback that is gonna be called select CPU and then enqueue and then something is gonna happen, okay? So this is wake up. This is the sort of regular case. On the other side, this is called balance, okay? Balance, what does it mean? Remember I told you that schedule is gonna look for tasks in those classes. It's gonna do in deadline, real time, fair, extensible. Oops, I found nothing, okay, empty. So this is when you call the Sched callback to balance, which is like load balance. Like I don't have anything to do. Can anybody else give me work? And so this is the balance, because if you don't find anything, you go idle. Okay. And in the balance case, this is what you do. So let's look briefly. I have 6 minutes. So we are entering the schedule. So we call schedule here. All right. Task is waking up because it could be a time slice exhaustion, okay? Task is waking up, yes. So I call select CPU. Select CPU, I get my task and I choose a CPU that I want it to run on. Then a migration happens. So your select CPU, like you return the CPU number, S32, signed integer, 32-bit, okay? You return it, the framework has its kernel code that poof, is going to migrate itself to the other CPU, and this task is now runnable. If it was not a wake up, I don't call the select, okay? And then we call the enqueue. Enqueue is, remember, Sched-Ext core enqueue, I take charge of the task, and So it's mine. Like mine, I am the BPF scheduler. And so I call enqueue, and in enqueue here, this is not this is not indicated, but now enqueue will want to call one of those helpers, in particular the dispatch helper. Dispatch helper that is going to send the task in one of, like, either on the exact CPU that was correctly guessed by select CPU or somewhere else. So task dispatch directly to CPU. Directly to CPU means to the local DSQ. So you see, when I told you that there are those local DSQ, it's important to know about them, because otherwise it's hard to understand those comments. I didn't write this. This is like official documentation. Directly to CPU. Like task and queue in the CPU's local DSQ. Like you need a little to decode that stuff. So, so I'm calling the SCX BPF dispatch directly to CPU. Done. It's over. No. It's on a different DSQ, somewhere else, remote CPU, or one of those custom ones, task and queued in the BPF scheduler. So now it's in the BPF module, and you have to take care of it, right? So 4 minutes left. So now it's the balance case. Like we are either iterating over the class, and we don't find anything, okay? So we want to get some work. We want to keep this CPU rolling, right? So the first thing, does the CPU have locally dispatched task, locally dispatched in the local DSQ? So first thing you look at is the local DSQ, which I think it's empty because it's balanced. So I'm not sure I understand correctly this diagram, but does have locally dispatched task? No. Okay. We call dispatch. Dispatch is a callback that I have to implement. And how do I implement? Using those two guys. Dispatch or consume. Dispatch, can call it many times. Dispatch means send this task to some DSQ. One that I want. Like we are not talking algorithms. I'm telling you what you can call. Then your algorithms will decide, oh, I have the DSQ for priority task, the DSQ for C group number 5. That's you, that's your stuff, that's your problem. And so you call it several times. Or consume. What is consume? Consume is kind of the opposite. It gets in argument, so unsigned integer 64-bit DSQ ID. This is like the identifier for a DSQ, for some other DSQ that is not the one on this CPU. So I consume, so there is a DSQ over there. I take the first task that's out of it, and I put it on the local DSQ of this CPU. So I replenish the local DSQ, which is the end goal, the terminal station, right? And I can do it as many times as I want, like boom, many times as I want. While on the other, like in the previous case here, enqueue, I told you that you do a dispatch, but you can do only one in this particular, like in this state, like the select CPU enqueue, just one dispatch. It's one task, the task that woke up, that you had to dispatch that one. It's the framework is made like that. 2 minutes. So dispatch, I can call SCX BPF dispatch. It's kind of unfortunate they have the same name because that's a little bit like not exactly the same thing. This is a callback, this is a helper. And so I call this a bunch of times, I consume a bunch of tasks, and then I go back. Finally, I check any task dispatch from the callback above. No, sorry, I go idle. If it's yes, then it's like, oh, it goes over here again. Do you have any locally dispatched task finally? Yes, I do. Oof. And it's in the local DSQ. Note, 1 minute. Note, we're not running the task. We deliver to the final DSQ. Then it's the Sched code that will deliver it like at some as soon as possible, I guess. Anyway, 1 minute. Any question? Because otherwise I need to leave the stage. Also, you probably didn't have lunch. I don't know. Yeah. So when you write BPF code, so that's right. Like, let's go here. So the BPF, so you write BPF code, and this code, it's like C, it looks like C. There are some, you can't have global variable and stuff like that, but it's like C. Then you compile it. It's bytecode now for a fantasy architecture that is actually a virtual machine in the kernel. Boom, you send it in the kernel, it runs in the kernel, all right? What I was referring to when I said user space is two things. Number one, a tiny C program that sends command line arguments to this guy. You're not talking about that. What you're talking about is writing a scheduler in user space, because the BPF scheduler, quote unquote scheduler, because it does nothing in this case, it's in the kernel, but it just exposes you the data, right? So what is the advantage? Is it faster? No, it's slower, all right? Most of the time it's going to be slower, but it's easier. So it's like more convenient. You have your familiar tool, like programming for BPF, it's kind of a pain, because you can't do this, you can't do that, you cannot call that function, you cannot do floating point arithmetic, you see what I mean? I cannot call like an AI to tell me what to schedule next or whatever, But if I do it in the user space, it's like I can do whatever. So it's like more empowering. I'm out of time, guys. Thank you for the question. Gonna wrap it up, maybe. By the way, thank you for your attention. Lots of silence. It's time. I'm saying that because it's 12:50, right? I'm supposed to end it now. Okay. So I really thank you for I saw that you were following. I trust my intuition, and I am very happy to have been here presenting in front of you. And have a good rest of the day. Enjoy the rest of the conference, all right?